All right, we're going live. All right, welcome everybody.
Awesome. Hello, hello.
If you guys have any questions throughout the show, please feel free to throw them in the chat. If Kate can answer them, she is manning the chat for us tonight. Otherwise, we will make a list of them and we'll have plenty of time to talk at the end. Oh, Alex is on. Francis, always good to have you on. Waiting to see who'll be the first to ask you what your background is.
Me or Shane?
Oh, either actually.
We can ask Katya what hers is.
I can tell you that mine is the Galaxy M94.
Nice.
I'm doing my first year research project on it, hence why I have it.
What exactly are you studying with it?
We're studying the stellar halo of M94 and also trying to discern some of its merger history, and also trying to see where its pseudo-bulge arose from.
Interesting. Alex. Oh, hello, Bob. Hello, Elias. Welcome. And that's phone telling me that this stream I'm subscribed to. Okay. So yeah. So behind Katya we have a big swirling galaxy, which is M. Oh wait, what is it? 94?
94. Yep.
Yes. Okay, good. I remembered.
Got it.
And then Shane, I'll have you describe your background in a second when we get started.
Okay, no problem.
Awesome. Your background. Right, I think we are ready to get rolling here. So, welcome everybody. It has been quite a while since we've had an episode of The Glass Room. We are really excited to be back, and we're really excited about our guest today, Professor Shane Larson from Northwestern, who's going to talk about probably one of the coolest projects I've heard about in a really long time. And of course, as always, I have my co-host Katya Gosman, who is now a graduate student at the University of Michigan, and the galaxy you see behind her is something she is actively studying in grad school. So if you missed that conversation before, we can maybe touch on that once more towards the end if anybody's curious. But with that, I want to hand it off to you, Shane. First, if you could just describe what exactly that thing is behind you, and then just go ahead and tell us what you want to talk to us about today, and we should just jump right in.
Okay, great. Well, thank you so much. Thanks to Glass for the invitation to come out and talk about things that are near and dear to my heart. I am a professor of physics and astronomy at Northwestern. I'm also the associate director of CIERA, which is our Center for Interdisciplinary Astrophysics. And we do lots of different kinds of research at CIERA. We work on exoplanets, we work on stars, we work on black holes, we work on galaxies, and we work on gravitational waves. And my research area is in gravitational waves. And so what I'm going to talk to you about tonight is a little bit about gravitational waves, but mostly about the future of gravitational waves, because I work on a mission called LISA. And so this is what's in my background here. So this is a rendition of the one of the 3 LISA spacecraft, which I'll tell you about in a moment. This is going to form a gravitational wave observatory that's in outer space, and we'll talk about that. And what I like about this picture is it gives you a very good representation of what the spacecraft we currently think it's going to look like. It's about 2 meters across, it's about 50 centimeters deep, and on the scale of a zoom screen like this, it's just a little bit smaller than life size relative to me. So it kind of, it's really big. And I've been in the hall with a model of this before, and you can sit on top of it and stand next to it, and it kind of feels like the image that you see here. What I like about this image is that it shows in the background, you can see the faint dots of stars, right? So those are stars that you can see in visible light. Light is the way that we traditionally study the universe. Virtually everything that you know or you've read about the universe, we've learned through the study of light, whether in ancient days it was, and still today, it's the use of your naked eye, or now with a wide array of different kinds of telescopes, but almost all of them are geared towards detecting some form of light from the universe. We're harnessing light in the form of these lasers that you see coming out of the spacecraft here. That's how we're going to make our measurements, and we'll talk about that in a minute. But what we're trying to sense is not light at all. We're trying to sense gravity, and we'll talk a little bit about exactly what it is we're trying to sense. And you see that in the background here, these big blue arcs are the representations in this artist image of gravity propagating through the universe, and LISA will ultimately detect this. So this is what we're going to talk about tonight. Katya is just starting her study on her background of the galaxy there. I started the study of my study of LISA when I was in graduate school. So I've pretty much done this my whole career. So this is really just my graduate work 20 years onward. And so in 20 years, Katya can come back and tell us about her galaxy that she's studying. So. Okay, so let me show a few slides. I'm going to talk for kind of 10-ish minutes or so, 15 minutes. I'm going to tell you about LISA and about the science that we hope to do with LISA. And then we'll turn it over to questions. As Adam said, if you spit those out into the chat, they'll pay attention. But then we'll leave, 40 minutes or so when we're all done to try and answer any of the questions that we have. Okay? So let me go ahead and share some slides with you. Okay, so can you see those? Yeah? Okay, I'm going to assume since Adam and Katya aren't saying no, they can see the slides.
You are good to go.
Yes.
Okay, perfect. So we're going to talk about LISA, which is an acronym. It's the Laser Interferometer Space Antenna. And what I love about the LISA name is it has all the different parts about what this mission is all about. It's an instrument, it's a laser interferometer, it's in space, and it's an antenna. It's trying to detect something from the universe. And so this has been the name for a long, long time. It's great. If I ever meet you out in public when we're doing real face-to-face talks and your name's Lisa, I give you a Lisa sticker so you can adorn your water bottle with a NASA logoed sticker. But this is what we're going to talk about. My email address is there. We'll certainly answer as many questions as we can tonight. But invariably 2 weeks from now, you're going to wake up in the middle of the night and you'll have some question you wished you had asked me. And your spouse does not want you to wake them up and talk to them about astrophysics at 2 in the morning. So send me an email and we'll do our best to help you find some answers to whatever question you had. There's a link to my blog. My blog is aimed at the public, or it's supposed to be. There's a whole bunch of different stuff there, but there is stuff about gravitational waves to read. As I tell people, I write for my mom, so she knows what I work on. So yeah, hopefully it's accessible. And then I'm there on social media if you want to chatter at me on social media. So this is, you've probably seen movies about gravitational waves if you've been paying attention to the astronomy news at all. They've been very big for the last 5 years since we made the first discovery. The first discovery was made by a ground-based observatory called LIGO and Virgo. Virgo is right outside of Pisa in Italy, and LIGO is 2 separate observatories, one in Hanford, Washington, and one in Livingston, Louisiana. And they were the very first observatories to detect this phenomena called gravitational waves. And LISA is going to be another observatory. It's just going to be in outer space. And one of the first questions people ask us is, if you can see gravitational waves with LIGO, why do you need LISA? And the point is that the sources that we're going to look at, and you're watching a movie here of the gravitational waves from two black holes colliding, the sources that we look at emit different gravitational waves at different phases in their lives, and different gravitational waves depending on what they are. And so just like we have radio telescopes, optical telescopes, and X-ray telescopes to see different kinds of light, all emitted by roughly the same astrophysical phenomena, say stars, we need different gravitational wave observatories to observe the different gravitational waves that we might get from, say, two black holes spiraling around each other and eventually colliding. Now, if you've seen movies of gravitational waves before, you've probably seen the most common one that people see is one that looks like ripples on a pond. But I like this one a lot better. This one was simulated by colleagues of mine at Goddard Space Flight Center, which is a NASA center in Maryland. And what I like about this one is that it shows the gravitational waves propagating outward from the source, in this case, two black holes hitting each other. And what I like about it is it shows the gravitational waves go in every direction, right? They're not just waves going out flat on the surface of a pond. They go in every direction from the black hole. And that's really important when you're doing astronomy, because it means you can be anywhere in the universe and detect the waves from this source. It's just like a star, right? The sun sends light off in every direction. So no matter where you are, if you are looking towards the sun with a telescope, you're going to get some of that light. And the same thing's true of gravitational waves. No matter where we are in relation to whatever it is that's making gravitational waves out there in the universe, we can detect them if we can build an observatory like LIGO or like LISA to sense them. The other thing I like about this movie is you'll notice that the gravitational waves are very complex, and it's that complexity of the waves where all the information about what it is that's causing the gravitational wave is stored. So if we can detect that complex structure and work out what it means, that's how we can tell you things about how massive the black holes are and how big their orbits were and were they spinning and all of those things that you hear astronomers talk about. Okay? So that's the story of what they are, and we'll come back to that point that I just made a minute ago. So this is LISA. So LISA is a planned observatory that will be in space. It will be comprised of 3 spacecraft. Okay, so this is a slightly different representation than the one right behind me. They are each 2.5 million kilometers away from the other one. So this picture is not to scale. These spacecraft would be enormous if this were to scale. Okay, but we had to make it so you could see them. The gravitational waves, if you can see it on your screen, there are these faint ripples propagating across the constellation, the 3 spacecraft as we say it. And what we're doing is we're shining lasers back and forth between the 3 spacecraft. We're basically timing how long it takes a laser to go from one spacecraft to the other. Okay, and so it takes about 8.5 seconds to get from one to the other. So that's fundamentally the measurement that we're trying to make. And we'll tell you why that's the measurement. Okay, so let me show you why that helps us measure gravitational waves. Oh, this is what LISA looks like if it's built out of Lego. I do Legos too, for those of you who want to know why there's Legos in my talk. So if you take general relativity is the study of the modern understanding of gravity. Einstein worked it out in 1915. In 1916, he predicted the existence of gravitational waves, and it took till 2015 for us to actually be able to understand what he meant and build an instrument capable of detecting them. But if you study general relativity and you study gravitational waves, the way we teach you about how we measure gravitational waves is we start with a picture like this. And what you should imagine is each one of those black dots is a marble that's sitting all by itself in outer space. And at any given moment, if I handed you a ruler, you could go measure the distance between any 2 of those marbles. Okay? Now, what we do with an instrument like LISA is we don't use a ruler, we use lasers. So imagine any one of those marbles is actually a LISA spacecraft. And instead of putting a ruler down, I shine a laser from one spacecraft to the other and time how long it takes the laser to make the trip. So functionally, that's equivalent to using a ruler because the speed of light is constant. That's something Einstein taught us a long, long time ago. So if I know how long it took the laser to get from one spacecraft to the other, and I know the speed of light travels at a constant speed, then I can tell you exactly how far apart the spacecraft are. So that's the measurement that we're trying to make. Okay, and so fundamentally, it's just this marble picture that we use in our heads to understand what gravitational waves do. So how does that help us measure gravitational waves? Well, what you do is you ask yourself, what happens when gravitational wave passes through this array of marbles that I've laid out? So imagine a gravitational wave propagating straight out of the computer screen at your face, okay? When it does that, it takes and it changes the distance between the marbles. And it does it in this very regular and repeating pattern that you see there. So this pattern is called the plus pattern because you'll see sometimes the pattern looks flattened horizontally and sometimes it looks flattened vertically. Okay, so when it's flattened vertically, all the marbles have been stretched apart in the vertical direction and pushed together in the horizontal direction. And then a little while later, they get pushed apart in the horizontal direction and compressed or pushed closer together in the vertical direction. And so if you imagine one of those particles, or three of those particles are the LISA spacecraft, like I've shown you on the left there, then this pushing back and forth of the marbles relative to each other is going to change how long it takes the lasers to travel between the three spacecraft. And that's the measurement that we are making, okay? Or we will make. LISA will launch sometime around 2030 or so. LIGO is making this measurement right now on the ground, okay? So let me show you a movie of the LISA mission concept. So LISA is 2.5 million kilometers across the triangle. So it has to be in outer space. It's far bigger than the Earth or anything we could put in Earth orbit. So it will follow the Earth around it as it goes around the sun. And it maintains this triangular shape. And what you're seeing right now is each of the spacecraft is on an orbit, a separate orbit around the sun. And we've just cleverly chosen those orbits so LISA maintains that triangular configuration. It's a very special set of orbits. They're kind of neat. And there's a unique set of them for which it maintains this triangular shape. Inside the spacecraft are these two telescopes. They're roughly the size of an amateur telescope that you would use in your backyard, but they're off axis, so they're kind of fancy. They're very fast. For those of you who know things about telescopes, they're high F ratios. They're like f1.5 telescopes. And the lasers both go out and in through the telescope. So the distant laser light comes in and it gets reflected into the back of the telescope there, where there's an optical bench. We also generate a laser on the optical bench and send it back out through the telescope going the other way. But the guts of the spacecraft, the heart, is to measure that laser light. Because remember, we're timing how long it took the laser light to get from one spacecraft to the other. And what we're actually measuring the distance to is a little tiny cube of gold and platinum, which you see right there, that's floating in the middle of the spacecraft without anything touching it at all. The job of the spacecraft is to shield that cube from everything in the universe, the solar wind, light, temperature fluctuations, anything you can think of, from everything except gravity. And so if gravity pushes the cube around, then the laser light can detect it. Okay? So I have a picture here, right? NASA doesn't let you do, NASA and the European Space Agency, they're doing this together. They don't let you do complicated things without showing that you know how to do complicated things, because doing complicated things costs a lot of money. So about 5 years ago, we flew a mission called LISA Pathfinder. Okay, so you can see the LISA Pathfinder down there in the lower left with three of my colleagues. That's Karsten Donsman, Paul McNamara, and Stefano Vitali. You can see that's an actual spacecraft about the size of the LISA spacecraft. So it's kind of the size of the one that's behind me here in the picture. And what I'm holding in my hand there in the lower right is a replica of the actual cube, which is in the upper right, that we flew on LISA's Pathfinder, and it will be the same cubes that we fly on LISA. They're made out of gold and platinum. Okay, they're made out of gold and platinum because it's very shiny and it reflects laser light. And it has special properties that allows it to not be very sensitive to the magnetic fields that you encounter in space. That's why we choose gold and platinum. But they don't let people like me and you hold gold and platinum, right? Because we get fingerprints on it and we lick it and drop it while we're taking selfies and stuff. So the one I'm actually holding in my palm down there is made out of tungsten. So tungsten is, those of you who have had tungsten in your hand, it's very dense and very heavy. It weighs almost exactly the same amount as gold and platinum. So that cube down there is life size. It's about 2 kilos and it's about 4 centimeters to the side. And it's the same size as the original LISA cube, okay? And that little dot there in the middle, the center of the cube, that's actually a pusher dot. We basically have these fingers where we hold on to the cube during launch, because when you're on a rocket, everything shakes around. And so we can't just have a cube flying around all by itself in the rocket. And then once we get to space, the fingers push it out and then they release the cube and leave it free floating. So that's what the little dots that you see are. Okay, so that's what LISA's all about. So about 10 years from now, 2030, 2031 to somewhere in there, we will launch. And then we're going to do astronomy. So let me spend the last little bit of time here talking to you about what kinds of astronomy we have to do. Now, one of the great truths of modern science isn't an endeavor that you do all by yourself sitting at your desk anymore. Right? You can see it in this picture. Stefano and Karsten and Paul, they're just part of a much larger team that you don't see in this picture. And I also am a part of a much larger team. So this is my group. So these are all my students in the lower 2 rows. And the faculty colleagues I collaborate with the most are in the upper rows there. So Vicki is at Northwestern with me. She is the director of the center that I'm in. She and I work on similar things. She's kind of a LIGO expert, where I'm kind of a LISA expert. Matt Benaquista is a colleague of mine who just retired, actually. He was at the University of Texas. Brett Bolin is a colleague of mine at Grand Valley State in Michigan. And Patty Perdue is a colleague of mine at Colorado College, Colorado Springs, Colorado. And then down at the bottom are all of my students in my group. This is my current group of students. Katie and Michael, the first 2 there. Katie's had her PhD for a couple of years now, but Michael just got his PhD, so they've graduated. But everyone else is a graduate student, an undergraduate, and Ellie Welch, Janine right there in the middle. She's just starting as a freshman at Yale, but she was doing work with me for all 3 years of her high school. So, and then my cat CIERA, who you can see there, always does work with me. Okay, so all the things I tell you that I work on, I never do alone. I work mostly with these folks. These are my colleagues who collaborate with me, but then I also work with a very large group of people who are associated with the LISA mission. Okay, so what sorts of things do we study? We study all sorts of things in my group, and probably the most important thing that we study, not the most important thing, the most common thing we study, is the Milky Way itself. So if you're lucky enough to live someplace where it's dark and you go out, especially right now at this time of year, right when it gets dark, you can see the Milky Way arching up out of Sagittarius and up over your head if the skies are dark enough. The Milky Way, that light that you see, is actually the light of 400 billion individual stars, most of them too faint to see, but the combined light makes this faint diaphanous glow that you can see in the sky. And so if you take those 100 billion stars and you ask, how many dead stars are there in the Milky Way? And in particular, how many dead binary stars are there in the Milky Way? There are something like 10 to 100 million dead binary stars in the Milky Way. And what I mean by dead is I mean the stars have evolved past the end of their life, and they are now stellar skeletons, typically white dwarfs. That's the most common, but some of them are neutron stars and some of them are black holes. And the point is when they evolve to that state of their life, they are very good sources of gravitational waves. And LISA can sense all of them. Okay, so this is arguably the most important source that LISA will observe, not because it's the one astronomers are most interested in, but because it's the one we're going to see the most examples of. There will be some 100 million of them maybe that are radiating together that will make this faint background hum of gravitational waves that you constantly hear from the galaxy. We often describe that as being at a party, right? When you're at a party, you just hear all the laughing and talking and everything going on in the background, but you can't make out all the conversations. But what you can make out are all the loud ones and all the ones that are really close to you. And so there will be about 10,000 of those that LISA will be able to individually. So what we do in my group right now is we simulate this. So this is a simulation of a galaxy that my group and I have done. And we're zooming out from the sun. And as we zoom out from the sun, the purple dots that appear are these individually resolved stars that you'll be able to see with LISA. And what you can see is that they are detectable across the entire Milky Way from one side to the other. And when we go edge on, you can see that they actually trace out the shape of the Milky Way. So there's a ton of astrophysics to be learned by looking at the stellar graveyard of the galaxy. Now, you'll see some various colors in there. In particular, you'll see some purple ones. Those are a group of stars that a colleague of mine and I, Tyson Littenberg, several years ago, we worked out. There are some set of these that you'll be able to see with LISA and with a telescope at the same time. So you can study those sources both with light and with gravitational waves. And this is something that we call multi-messenger astronomy. And it's very important if you're going to try and understand the stellar lifetime of these stars. Now, the black dots there are the ones that we already know about. We can see them in telescopes, and we know enough about their properties that we know they're going to be strong sources for them. So this is why we know we can. Many of those black dots have been discovered and well characterized by amateurs. And so if you're an amateur photometer and you like doing measurements in your backyard, some of these LISA sources you can measure from the backyard. Okay, so that's one thing we study. Another thing that we study is something called an EMRI, an extreme mass ratio inspiral. So in the center of most large galaxies, like the one behind Katya there, deep in the bulge, there is a massive black hole or a supermassive black hole. And one of the great mysteries of the cosmos is, how do those black holes grow and how do they influence the environment around them? Well, if you look at our own Milky Way, we see lots of stars down in the vicinity of the Milky Way. This is what the recent Nobel Prize in Physics was given for observations of those stars by Andrea Gheze's group at UCLA and Reinhard Genzel's group in Europe. But every now and then, one of those objects should fall into the black hole. And when it does, it will trace out these very exotic orbits like the one you see going through here. And those will be emitting gravitational waves that LISA can measure. And by measuring the gravitational waves, what you see is, because they're going virtually everywhere around the black hole, we can tell you in exquisite detail about the gravitational structure that the black hole has, basically its influence on the area around it. And that allows us to understand, does it look exactly like the mathematical description of black holes that general relativity predicts? It allows us to measure the mass of the black holes. It allows us to measure the shape of the black holes. It allows us to measure if they're spinning. All of the properties of the black hole are encoded in these exotic orbits. Okay, so we study this in my group as well. And then the last thing is, if we look out in the universe, we often see that galaxies collide. And there are lots and lots of examples of galaxies in collision that you can see. This is a particularly famous example called the antenna galaxies in Corvus. If you have a good size amateur telescope, 12, 16 inches or so, these should be easy targets for you, especially if you can get out under dark skies. But it's basically two galaxies that probably early in their lives were not unlike the one behind Katya. But now they've come close enough together that they can see each other's gravity, and you can see it's distorting them in very exquisite ways. And so you can see those long tails behind them. Those are the famous antennae. We call those tidal tails. They're basically streams of stars that are being ripped off of the galaxies and left behind. And eventually, those two galaxies will merge. They will form a football-like galaxy, not a spiral-shaped galaxy like they started like. That football-like galaxy is called an elliptical galaxy. But the important thing for us, for those of us who study LISA, is that these galaxies had black holes at the centers of them. So when the galaxies merge, eventually the black holes will sink down towards the center. And when the black holes sink to the center, eventually they find each other. And when they find each other, they spiral around each other and emit gravitational waves and eventually merge and become one bigger black. So if you talk to someone besides me, they'll tell you this is one of the most exciting things that we will study, because this allows us to study the merger of those big black holes anywhere in the universe. We will be able to see black holes merging all the way to the edge of the visible universe. There's no place in the universe these sources can hide from. Okay, so that's really cool. So that's just a really high level view of all the different things that LISA might study. But the point in this is that all the gravitational waves we get from any of these sources are exquisitely different than the gravitational waves we get from some other source. They change depending on what the sources are. The gravitational waves from white dwarfs look different than the gravitational waves from black holes. They change depending on the mass. They change depending on the spin. They change on whether or not the orbit is elliptical or round. They change on if the orbit is tipped to your line of sight or edge onto your line of sight. All of that information is encoded in the waves. And so when you study gravitational waves, you spend a lot of your life looking at pictures like the ones I'm showing you here. And if you stare at them long enough, you can look at them and know exactly what I'm showing you, okay? But for the general public, right, we've all learned about the universe through the eyes of Hubble, right? We're used to looking at pretty pictures like the one behind Katya. And so when I make a gigantic gravitational wave discovery and I send one of these graphs to the editor at the Chicago Tribune, they're like, go away, kid, you bother us. Okay, and so that's really frustrating because we think this stuff is really, really, really awesome. And so we spend a lot of time thinking about how do you help people understand, really in a visceral way, understand that there's awesome gravitational wave information in these signals. The way we've kind of settled on doing that is we can take these signals and we can turn them into sound. Right? And you're all used to this. Right now on your iPhone, there's a whole bunch of wiggles stored on your iPhone that when it gets pushed out through the headphone jack, your iPhone plays Katy Perry or Led Zeppelin or Glenn Miller Band or whatever it is you listen to, okay? But if I stole your iPhone while you were busy watching this YouTube live and I replaced your Katy Perry with these wiggles, when your headphone pushes it out through the jack, you're going to hear sound that isn't Katy Perry. It's the gravitational wave signals represented as sound. Okay, so it's just a way of making your human senses able to understand this natural phenomena that your body has no physical sensory apparatus to detect. So to end here, I'm going to play two different gravitational wave sounds for you. We could play sounds all day long, but I'm just going to play two for you. And I've chosen these two for a very specific reason. These two are exactly the same system. They're a small 10 solar mass black hole spiraling into and merging with a 10,000 solar mass black hole. So they're similar to those emeries that I showed you a movie of just a minute ago. Now, the two sounds are the exact same two black holes, and the only thing I changed before I made the sound was one of them is on circular orbits going to smaller and smaller circular orbits until the black holes merge. And the other one is a highly oval-shaped or elliptical-shaped orbit that the black hole goes on as it slowly moves to the big black hole. Okay, and what I want you to notice is you can absolutely 100% hear the difference between these. If I just played these on headphones, you'd be like, whoa, those two things are different. But if I just gave you a list of numbers that said 10 solar mass black hole, 10,000 solar mass black hole, you might look at those and be like, what's different about these? But your ear is an exquisitely trained scientific instrument. You've trained your whole life being able to recognize that one sound is different than another. And so this demonstration kind of illustrates. Okay, so let me play these two sounds and then we'll wrap up and take some questions. So this is the circular orbit one. Okay, so we call that a chirp. So what's happening? When the orbit's big, long before the black holes merge, the pitch is low because the pitch, the frequency that you hear, is related to how fast they go around their orbit. But the gravitational waves make the orbits shrink, and as orbits get smaller, the objects go around their orbit faster and faster and faster. So you're familiar with this from astronomy. The Earth takes a year to go around its orbit, but Mercury only takes 88 days to go around its orbit. So as orbits get smaller, they go around faster and faster. Okay? Now I'm going to play the second one. And remember, the only difference here is the orbits are oval shaped. They're elliptical.
I think we lost the sound.
Can you not hear it?
Only while you were talking.
Oh. That's interesting. Could you hear the first sound?
I think we heard most of it, and then at the end, the chirp was kind of silent.
Oh. Okay, well, I am prepared for all eventualities. So I also have these on my phone. They spin up in the middle of my playlists because you know it's the sounds of the universe, right? Let's see here. Let's see if I can pull them up and play them by just holding them up to the microphone. The Lisa playlist. I don't even know where my microphone on my computer is. You hear that?
Fades away.
It fades away, so it's only paying attention when I talk. Yeah. Oh, here, let me try one other thing. I bet I can't do it. I bet I can't do it while I'm sharing.
Yeah, I think Bob was right. The noise canceling is masking it.
Yeah, so here, I'm going to share my computer sound. Let's see if it'll work again if I share my computer sound. Okay. So right now it's sharing. Okay, tell me if you can hear it this time. Okay, that was the first one. So let's try the second one again. Okay, so the second one's the oval-shaped orbit. So what's going on in the second one is that when the orbit is really oval shaped, sometimes the black holes are close together and sometimes they're far apart. And when they're close together, the gravitational waves are strong and you hear that pop. But then when they're far apart, the gravitational waves are weak and so you can't hear the sound. And then they pop and then there's quiet, and they pop and they're quiet. And as time goes on, gravitational waves have a tendency to force the orbit to be more circular. And so it ends up being very similar to the original sound as it gets. Okay? Okay, so that's all I was going to say. So I always like to leave you with a few things to go read on your own. There are no good books about Lisa yet because Lisa hasn't flown. But the book there on the upper right, Einstein's Unfinished Symphony, was written by Marcia Bartusiak. So Marcia is an excellent science writer. You may have read many of her other books. She's written about the Big Bang and the discovery of the universe and all kinds of different stuff. But this is her book about gravitational waves. It's largely about the construction of LIGO. The book comes in 2 editions. So if you get the most recent edition, she'll also talk about the recent gravitational wave discoveries. So that's definitely look for that if you get it from your library. Black Holes and Time Warps is a book by Kip Thorne. It's his public level book about gravity, gravitational waves, wormholes, black holes, all the exotic relativity stuff. Both of these books by Marcia and Kip have won science writing awards. So they're really excellent books to refer to. And I highly commend your attention. If you'd like to participate in gravitational waves, there's a great citizen science project that we've developed here at Northwestern with our partners at Adler, Syracuse, and with the folks at LIGO. It's called Gravity Spy. And basically, we need your help looking at LIGO data, which is what that picture is right there, and identifying signals that all kind of look the same. And the reason we're doing that is we're trying to teach the computer what to do and what not to do. So we have humans look at a whole bunch of these signals, and then we take them to the computer and say, see, this is what we mean, do it right. And so it's part of this kind of big artificial learning experiment that we're and then there's some links there to my blog and some things that I've done about gravity and gravitational waves. So if you want to link up to some of the stuff that I've written about and done. Okay, so I'm going to end there and say thank you so much. And hopefully the sound glitching there wasn't too much of a distraction, but I'm going to hand it back to Adam and Katya, and we'll take some questions.
All right, man, we already have one question in the chat. This comes from Bob. He says,
hey, Bob.
3 LISA satellites define a plane. Does that still give you 3D images, or do you still need a 4th satellite to get directional information?
Yeah, so that's a great question. So with a gravitational wave detector, if you were to just get a signal that passed through the detector and then went on, you would not be able to localize it very well with one. Okay, so with LIGO, this is actually the problem, right? If we just had one LIGO, we'd never be able to tell where it came from on the sky. But we have the 2 LIGO detectors and the detector in Europe, soon the detector in Japan, and there will be a 5th one in India. And so when the gravitational waves come by, they hit one detector first, and another detector second, and another detector third. And so we can triangulate and say it came from over there. With LISA, all 3 satellites are one detector. So we don't have that kind of directional capability. The difference is for LISA, the sources that we're talking about observing, all the ones that I told you about, they last for a long, long time, a year or more, or even for the entire time that LISA will be observing. And so you'll remember LISA goes around the sun. And so the fact is sometimes we observe when LISA is over here, and sometimes we observe when LISA's over here, sometimes we observe when LISA's over here, and that's what gives us our directional capability with LISA.
Gotcha. That's really cool. So it's almost kind of like using I'm blanking on the term. Katya, help me out. Astronomy 101, using measurements from one side of our orbit to the other for distance to stars.
Parallax.
Thank you.
Parallax, yeah. It's kind of like parallax, actually. It's really, yeah, triangulation is kind of the Earth-based version of what astronomers do when they measure parallax, because it's all about angles and baselines, right? Yeah.
All right, Katya, did you have any other questions? Or I've got one of my own.
Yeah, I do. So in your simulation, you had one that was like a circular orbit and one that was an eccentric orbit. What determines whether something is orbiting in a circular orbit or in an eccentric orbit?
Yeah, that's a great question. So the reason we study these things in my group is because we're interested in using, and this is actually what all astronomy is about, right? I go out and I make some observations. And one thing we do when we make observations is we tell you what are the properties we know about because of those observations. So we're going to tell you the mass of the stars, and we're going to tell you the size of the stars, and we're going to tell you how far apart they are, right? All of that. So those are what we call parameters, right? And if you were measuring ordinary stars, we'd tell you, you know, what's its stellar type and what's its surface temperature, how bright it is and how far away it is. But what astronomers are really interested in is all the things about the star that made it the way it is. And so if you study stars, and you've done this in normal astronomy, you'll often resort to something like the HR diagram, and you'll talk about how a star lives its life and it moves around the HR diagram. So, you know, it starts here and then it moves to the main sequence and it burns hydrogen and helium and then it becomes a red giant, it becomes a white dwarf, right? The way we work that out is we studied a gazillion stars and they're all at different stages in their life, and then we made the HR diagram. So with LISA, we're doing the same thing. We're going to study a gazillion stars, but our goal is to understand the evolutionary history of the stellar graveyard. And so the point is that sometimes in their lives when they're born with some eccentricity for whatever reason. So a classic example is imagine two stars in a perfectly circular orbit, and then one of them goes supernova to create a neutron star. Well, that supernova gives one of the stars a big kick. And when it does, it distorts the orbit. It might even break the binary up, but let's say it distorts the orbit, and it ends up in an elliptical orbit, right? Well, over time, for instance, gravitational waves, there are other astrophysical processes as well, will make that orbit circular. And so measuring that eccentricity, as we call it, that oval shapedness, will tell us something about the evolutionary history of the stars. And it may be every one of them we look at is circular, right? But we know at some point they were elliptical. So that means the universe is very efficient at making things elliptical or circular. But if some, 10% of them are elliptical and 10% are half elliptical and all the rest are circular, that tells us something different about the astrophysics. So this is what we're trying to learn. But that question is exactly the one we sit in our group and talk about all the time. What will make an orbit elliptical and what will remove that ellipticity from it? And then how can we use LISA to understand those processes?
We can kind of figure out the history of the star and its surrounding environments, I guess, from LISA.
Exactly.
That's super cool.
And you have to do that in astronomy, right? This is the whole point in astronomy, right? If every other science, if you're a geologist, right, you can sit at home like you and I do and be armchair geologists and talk all about, feldspar and granite and stuff. But at some point, you can go out with your rock hammer and get a piece of it and take it back to the lab and work on it, right? But with astronomy, we can't do it. We literally have to be armchair scientists when we're astronomers. All we can do is sit here on Earth and look. We can't do any experiments. We can't measure the environments. We can't go do the chemistry. We can't physically measure the temperature. We have to sit here and only with what we observe, infer all those properties about what's going on so far away in the universe, no human will ever visit. And LISA, this is why it's so important to build new instruments like LISA, is because they're going to tell us something completely different than what a telescope tells us. And having two completely different sources of information helps you infer, deduce what the weird universe is doing infinitely far away.
So then once LISA is launched, will there be times where they send out targets that they want certain telescopes to go and observe?
Yeah, so all the gravitational wave observatories and the ground-based observatories, the LIGO, Virgo, Kagra network, Kagra is the Japanese detector. LIGO, Virgo, Kagra right now sends out alerts. So anytime they've seen a big source that might have an electromagnetic counterpart, they send out the alerts, and the astronomers around the world who have time on telescopes, they wake up at 4 a.m. and go get their cell phone, and they see, okay, is this worth putting the telescope on? And sometimes it is. So in 2017, we discovered the binary neutron star merger. Okay, so that was two neutron stars that were coincident with a short gamma ray burst. And we saw it with LIGO, and within 12 hours, we had 70 telescopes in the world on it as well. And so that multi-messenger detection allowed us to, in very real ways, characterize that source. And so now this is the way astronomy works, right? Gravitational waves are part of the astronomy toolbox. And so alerts go out, and this will be even more true in LISA, because with LISA, we're going to send out alerts about supermassive black holes emerging. And everyone in the world wants to see two gigantic black holes merge because it will be the strongest gravitational wave event we've ever seen. And you definitely want to have your X-ray telescope looking at it just in case there's some light that we can see from it. There's good apps. If you go to the app stores, there's good apps that you, ordinary people, not just people with giant telescopes, can get those alerts on your phone too. So if you want to run out in your backyard with your amateur telescope and see if you can see it, there will be some that amateurs can detect, but the alerts are open and public, whether you're an astronomer or not.
Awesome. All right, we have another question in the chat. This is from Alex. For the sonified gravitational waves, does volume and pitch both represent different information, or does it only use pitch?
So that's a great question. It uses both. So the snippets that I played for you are kind of the last 30 or 40 seconds of a much longer waveform that I can play. That longer waveform, it's at lower amplitude earlier in the wave. And so that corresponds to the strength of the gravitational waves being weaker. You can hear them if you wear it with headphones, but if you're not using headphones, you can't hear it, which is why I don't play it in a public venue. But the amplitude of the gravitational waves combined with the pitch, those two numbers together are necessary for disentangling all the information about what the properties of the source that's making the gravitational waves are. So, it's the sort of thing that tells us how far apart are they, and how massive are they, and how far away from the Earth it is. All of that information is tangled up in those two numbers.
Awesome. All right, I don't see any other questions in the chat, but I've had one question that I've asked about. So, as Katya is currently studying galaxies in grad school, how did you end up, when you went to grad school, getting into the area of gravitational waves?
That's a great question. So there's actually a funny story to do with that, which I like to tell because I think it illustrates the importance of mentors in our lives, right? So I went to grad school to study black holes. That's what I wanted to do. And so I was a graduate student at Montana State University. My advisor was Bill Hiscock, who sadly has passed away many years ago now. But I had decided I was going to study black holes, and he and I had ended up during grad school interviews talking on the phone for multiple hours at a time. And I was like, okay, I'm going to go study black holes with this guy because that was awesome. So I went to study black holes with him, and I started early on working in a exotic but important sounding field called quantum field theory and curved spacetime, where basically we try to combine things that we understand about quantum world with things we understand about relativity. But it's intensely mathematical, and it's very esoteric. It's absolutely crucial and important if you want to understand quantum gravity, and if you want to understand the kind of fundamental nature of why gravity works. And I was studying black holes. That was great, but it taught me that what I really went to grad school to study was astrophysical black holes. Why are they important out in the universe? And so the funny part of this story that I like to tell people is that Bill and I were at a meeting. We had gone to an American Physical Society meeting. That's our professional society in physics. And we were riding back from the evening banquet on the bus. And it was like a school bus, like it's going on a field trip when you're in school, but it's full of physicists, right? And physicists, you may not think it, but we're rowdy, rambunctious people. And when you put a whole bus of physicists together, they're all laughing and joking and telling jokes about superconductors and stuff, and you just can't hear anything, right? It's just a cacophony. And I was sitting next to Bill's very first graduate student, a guy named Tim Olson, and Bill was sitting like 4 seats ahead of us, right? And I swear there's no way over all the physics jokes he could have heard us talking. But Tim was asking me, how are things going? Are you enjoying it? And I was like, yeah, it's fun. I'm learning about black holes, but I really want to do astrophysical black holes. I want to do this gravitational wave stuff that I keep hearing about, right? And literally the moment we got off the bus, Bill's like, so I hear you want to work on gravitational wave stuff. And I have no idea how he heard me. So this is what advisors do, right? Our goal is not to get you to work on something we want you to work on. Our goal is to help you find what you're passionate about, because that's what's going to make you get up and do physics every day when you get up in the morning. And so he and I sat down when we got back to Montana State, and we picked a new project for me, and I've been doing gravitational wave stuff ever since. Interestingly enough, I'm starting to work in quantum field theory again, but using gravitational waves to talk about it, which is kind of an interesting pivot in my life. So if I hadn't have done that early work, I wouldn't be able to do it now. So it all works out in me.
Wow.
Yeah, that is a really great story. Now, we've already had you for an hour, and there are 2 questions left. So if you want, we can have those forwarded to an email, or do you want them now?
Let's take the last 2 questions, and then we'll wrap it up.
Perfect. All right, so this comes from Elias. Overall, would the applications of this method of analysis further enhance some predictability of stellar life cycles?
Yeah, that's a great question. So this is something that we are working on right now. And in my group, what we do is we simulate the entire Milky Way galaxy. So we basically put in at the top of our simulation, all the stars that formed and when their birthdays were and how massive they were and were they with another star, blah, blah, blah. And then we evolve it forward in time till today, and we look at what the galaxy looks like. So because we're creating the galaxies from scratch, we can control the stellar lifetime. So we can change the properties of the galaxy, and that changes the stars that are alive at the end. So it may change the total number of stars. It may change the orbital periods that they all like to sit at. It may change the overall mass ratios of them. And so the idea is, what we're working on right now is that if I create these numerical models of the Milky Way, and then I just kind of keep them here on the corner of my desk until Lisa flies, someday, someone's going to walk in my office with the Lisa data and throw it down on my desk. And I'm going to take their graphs and I'm going to hold them up against my graphs and see which one of them matches up. And whichever one matches up, I'm going to be like, that's the way the stellar life in the galaxy works. And I'll know all the things that we put into it. What was the ratio of hydrogen to calcium in the galaxy? And how many big stars versus how many small stars formed? And were they all born right in one big burst at the beginning of the galaxy, or were they smeared out over the entire history of the galaxy? Right? Those are the kinds of questions we'll be able to answer. But it's about the kind of global properties of all the stars together that will be able to elucidate the answer to a question.
Awesome. All right. So the last question comes from Bob. What is the low threshold of what Lisa will be able to detect, and will it be able to detect binary objects without mergers?
That's a great question. Yeah. So let me answer the first one. So the threshold is a weird question to ask because there's a whole bunch of physics combined into that. So typically what we define is we say, tell me what you're interested in, and then I'll tell you the farthest away that Lisa might be able to detect such a source. Okay, so we call that the horizon distance. So like I said, for supermassive black holes, we can detect them all the way to the edge of the visible universe. Okay, so there's no black hole that we won't. For white dwarfs, for the heaviest white dwarf stars, I have a colleague, Valeria Carroll. She's at the University of Birmingham. So she had a paper a year or so ago where she showed that we should be able to see between 1 and I think it's 10 of those in the Andromeda galaxy. So we'll be able to see them completely throughout the Milky Way, no problem. And she's been looking at how far away can we see. So it's kind of different. It depends on how massive the objects are, is probably the single most important factor. So the big black holes we can see really far away because they're big, they're heavy, so their gravity is really strong. Okay. The second part of that question is I've forgotten now. What was the second part?
The second part of the question is, will it be able to detect binary objects without mergers?
Yes, so yeah. And the answer to that is absolutely. All of the binary stars in the Milky Way, none of them will merge during the LISA observation. White dwarfs going around other white dwarfs, they last for longer than the age of the universe typically. So none of those are expected to merge during the LISA observation. So those are absolutely binaries and they don't merge. So, which is different than what our colleagues in LIGO see, right? Everything that our colleagues with LIGO observe does merge. But for LISA, we'll have some, like the big black holes, they'll kind of slowly spiral together over the course of a year and then merge. The MREs will kind of zoom around in that exotic orbit for 1 or more years, and then they'll merge. But the white dwarf binaries, they won't merge at all when we're okay. Okay, that's a great question too.
Yeah, a lot of great questions tonight. Jane, I just want to say one last time, we are so thankful that you decided to come and join us tonight. This was an awesome presentation. I think we all learned quite a bit, and now we've all got some books to go buy on Amazon.
Yeah, there you go. Perfect. So thanks for the invitation. I really appreciate it. So good luck studying, everyone, and stay safe, okay?
Thank you. Thank you. That was
Okay.
great. And
Thanks,
to
guys.
everyone else who was watching, thank you so much for joining us again. Please join us. I think it's 2 weeks, in 2 weeks. Yep, to hear another presentation from another Northwestern professor, Raffaella Margutti. So heads up for announcements on that.
Yes, a lot of good content from us in October.
Yeah.
All right. Thank you, everybody, and have a good night.
Good night.